and instrumentation science. Thank you, Craig. And that kind of two-part dissertation project is a real challenge. And you'll see that there are similarities. Not only is one of the projects kind of the motivation for another project, but as you dig deeper down, you see that there are a lot of commonalities in the kind of the basic signal in the data and how we analyze it and pull the answer out. We've talked a little bit about these kind of commonalities as you progress through the projects. It's a bit academic because when you think about it in a practical sense, the different communities talk about the same things in very different ways. They approach the analysis, they have different tools. And so as part of Ryan's dissertation, he had to kind of jump between the two projects and become fluent in the two different communities' languages and how they approach the same problems. I'll add that being able to switch between different communities, applying the same kind of thing is really common. That's what graduate school is about, is learning how to take what you know in your basic math and physics and apply it to new science problems. So in that sense, Brian, you've done a very good job. Congratulations. So I will add also that I really enjoyed watching you kind of grow and develop and see how you could kind of context switch between the two projects. That was really enjoyable, and I learned a lot from you, so I thank you for that. I guess the one thing I gave you in return was I gave you the opportunity to shovel snow at 14,000 feet off the roof of the 88-inch. So this is a picture of Ryan, Luke, and I, and that is a pickaxe in Ryan's hand. So I hope the trade was worthwhile. And with that, I'll let you take it away.
All right, thank you, Mark. Thank you. Yeah, the trade was definitely worth it. This is one of my favorite memories from our observing runs.
We didn't get anything else done.
Yes, we did not shovel enough to open the dome, but we did shovel some snow. All right, so thank you everybody for coming today to my dissertation defense, the title of which is Spinning Red Clocks in Crowded Fields. There's a lot of ground to cover, so I'm going to dive right in. It's been a while since my proposal, so I will quickly remind you that the project is split into two parts. We have the science and the instrumentation work. On the science side of things, the goal was to further our understanding of M-dwarf spin down. And we did this by using a campaign of monitoring the open cluster M67. On the instrumentation side, the goal was to improve upon existing high resolution wide field imaging techniques, keeping in mind that we want to push the ability to do further deeper observations of clusters to continue the work that we've done with M67. And we did this by developing a new approach to tomography that's targeted specifically at ground layer adaptive optics. So starting with the science side of things, I'll just quickly remind you why we care about the ages of stars. If you're interested at all in galactic history, you obviously have to know how old the stars you're looking at are. So a great example of this would be if you're looking at the chemical evolution of our galaxy. And I want to point out that the M-dwarfs are extremely good for this. They have very long lifespans, and they're the most common type of star in the galaxy. So they're particularly good for studying something like galactic history. Zooming in a little bit, there's also planetary formation. Right, if you want to track the history of planetary formation in our galaxy, you're going to need to know the age of the host star. And again, M-dwarfs are really good for this. They're the most common host of Earth-sized planets in our galaxy. The question then is, how do you get the age of a star? There's a variety of approaches that exist, and they kind of fall into these two broad categories. On the empirical relation side, we have things like lithium abundances, the peculiar velocities, the age metallicity relation, or even the age activity relation. And on the model-based side, we have approaches that include things like isochrone fitting and astroseismology. Problem is, none of these actually work for M-dwarfs. Right, for M-dwarfs, the lithium is burned way too quickly to get a good lithium age for anything that's too old. Peculiar velocities only apply to populations of stars. So if you're interested in an individual star, you can't use that to get the age. The age metallicity relationship has flattened out over the past few gig years in our galaxy. And there's also some systematics you have to deal with where you form in the galaxy. And then finally, for the empirical relations, there is some cycle ambiguity. So where you are in the stellar cycle is going to impact the age that you get for an age-activity relation. On the model-based side, the evolution of M dwarfs on the main sequence is imperceptible. And finally, the oscillations that you need for astroseismology are immeasurably small for M dwarfs, which means we have to throw out all of these methods for when it comes to getting the ages of M dwarf stars. Fortunately, there is still some hope. Turns out all stars spin, and they do this because they acquire some angular momentum from the molecular cloud that they're born out of. In addition to this, they emit stellar winds, and these winds themselves are magnetized. And so what happens is you get an interaction between the stellar wind and the magnetic field of the star, and it applies a torque that's opposed to the rotation of the star. And in the end, you find that in general, an older star will spin slower than a younger star. I want to take a moment, because this is a very simplified version of this picture, and highlight that the details are actually very complicated, right? We're depending on the magnetic field of the star and the mass loss of the star, both of which are well characterized as poorly understood. That said, we do find that this picture generally holds. So I have here a sample of stars taken from various open clusters in our galaxy. And we see that as you go from the bottom to the top, you're moving up both in terms of, or you're moving to slower rotation periods and also to older stars. There's another feature on this diagram that I want to emphasize though, which is that each of these stars of a given age all seem to fall on a very tightly well-defined sequence. This is critical for getting ages from the rotation period for a couple of reasons. The first is that the fact that the sequence is very tight implies that the age that you can get from the rotation period can be very precise. The other important factor here is that this implies that the stars will forget their initial conditions, right? Because all the stars in a cluster are born with a wide range of initial rotation periods, and yet they have spun down in such a way that they've converged onto a tight sequence, and that sequence then evolves forward in time. So we'll take a crack at trying to describe this spin down, and we'll start with some simplifying assumptions. We're going to work with what we call the solid body models. In this case, you treat the star as a solid body in terms of its rotation, which is to say the whole thing is rotating with the same angular velocity. Usually what this gives you is a spin down that follows a Skumanich-like spin down law, which is to say the rotation period is proportional to the age of the star to some power. The commonly accepted value these days is 0.62. That's calibrated using sun-like stars in the open cluster Praesepe, which is the cluster in orange here, and then designed to give us a replication of the sun as it is today. Oh, apologies, I forgot to order my slides. So we'll go back to this diagram. It turns out it gives us a pretty good description of this spin down, despite the fact that we have all these underlying complications that we don't really understand just yet. The question then, because you may have noticed, I cut this figure off at K0 in terms of the stellar, the spectral type. What happens if we extrapolate this behavior to the lower mass stars? And that's a problem. We can see here, particularly this region of the diagram, the stars of different ages now overlap on this diagram. It's particularly bad for those M dwarfs at the NGC 752. This is telling us that these stars have spent a significant fraction of their life spinning at the same rotation period, which implies, just naively, that they're not losing angular momentum that whole time. That's not great. It's also very surprising that that happens. You can try to think of a variety of different ways that you might explain this. You know, maybe the magnetic fields turn off for some reason for a while. Maybe the mass loss changes, but there's a variety of different ways. We're going to try to figure out how we can explain that. So we'll revisit our solid body model. And now we're going to relax the assumption of it being a solid body. So this means that we're going to allow the angular velocity to change as a function of radius in the star. And this is going to enable us to produce some more complicated spin down over time. I'm going to highlight a particular case for the differential rotation model. This is the core envelope decoupling theory. This is a two-zone rotation model. So we have the core and the envelope that are themselves solid bodies. and we have a mechanism that allows them to exchange angular momentum. What this leads to is you have an early epoch of quick spin down. So the envelope is able to spin down because it's weakly coupled to the core. It sheds its angular momentum through this magnetic braking process. Then eventually you'll enter this era of recoupling. So the core will begin to transfer its angular momentum to the envelope and counteract the loss of angular momentum from the magnetic braking. This means that we have a potential explanation for why those stars stall their spin down. It's not that they're not losing angular momentum, it's just that the envelope is not losing angular momentum. It's still losing angular momentum from the core in this picture. Finally, the two will fully recouple, they'll equalize in their angular velocity, and the star will spend the rest of its life spinning down as a solid body. So I'll note that that means the two models that I've talked about are not mutually exclusive. So we'll revisit our diagram one last time. And as I've said, it provides a pretty compelling story for why we see that spin down, that stalling in the spin down. But as I've mentioned earlier in the talk, we're really interested in the M-dwarfs. And I want to highlight this region of the diagram where the M-dwarfs would exist if there were really any for us to use as calibrators. It's a very empty region. There's just a handful of M-dwarfs in this region that are older than the age of Chrysope, which is about 700 megayears. So any behavior for older M-dwarfs at the moment of this diagram is entirely extrapolation. And that is where M67 comes in. It is an open cluster in our galaxy that's 4 gigayears old. It's approximately solar metallicity, which means we're not going to rock the boat in terms of the composition of these stars compared to our other calibrators. Its distance is 880 parsecs, which is relatively close by in the grand scheme of things. That's important because we're going after the M-dwarfs, which are very faint. So the closer they are to us, the better for our observations. And we'll determine the membership in this cluster by using our Gaia EDR3 astrometry. And that's what we've done here. So I've taken all that astrometric information, and I've put it into a clustering algorithm. So we have the proper motion in RA, the parallax, and the proper motion in DEC. I have 3 scatter plots of the different combinations of those parameters plotted against each other, and then a histogram for each of them individually. In color are the members of M67 that we've identified with this clustering algorithm. And then in gray is, for comparison, the field stars, the distinct population of everything else in the galaxy. And you can see, particularly in proper motion in RA, that we've identified a population of stars here that are very well defined and distinct from the rest of the stars in the galaxy. This is how we know we've identified those members as being, those stars as being members in M67. We can follow up on this by checking to make sure that when we put them onto a color magnitude diagram, they form a nice clean main sequence, which is actually what we see. So I have 2 versions of it here. On the left is the pan-stars R-I colors. On the right, the Gaia G-RP colors. In color in both panels are the stars that we've identified as the main sequence, single stars. And in gray are basically the rest. So this includes unresolved binaries, some of the more evolved members of M67, things like that. And the reason I have the 2 of these here is the Gaia colors allow us to see that main sequence turnoff. It helps us understand that we are definitely looking at a cluster of stars. And the pan-stars colors are the ones that I will use for deriving effective temperatures, right? Because we want to know the physical parameters of the stars that we're studying. The most important of those is the effective temperature. And the pan-stars photometry is more precise for our faintest members than the Gaia photometry. And that's why we use that for our effective temperatures. So then we get into the real meat of the project, which is what we did. We monitored M67 with CFHT megaprime. So we collected Sloan I-band photometry that spans roughly 3 years. And we achieve a relative photometric precision of about 1% for our faintest members, so even better for some of our brighter ones. If we use these light curves to measure the rotation periods by Lomskargel periodograms, we have to use these because our data is very irregularly sampled in time. And so to make sure we're getting the right result, we do extensive amounts of verification. This includes a batch of injection and recovery testing. In the end, we find that we get about a 10% precision on the rotation periods that we recover. What does that look like for a single target? Well, I've got here in the upper left, I have the light curve itself for this star. In the bottom left is the light curve, but now phase folded to what we've detected as the rotation period. So this form is what really highlights the periodicity in the data that we've identified as the rotation period. On the right is the periodogram itself. The highest peak in the periodogram is what we take as the rotation period. And then I also track the aliases associated with that, which are denoted by the dotted lines. If I do this for all the stars in the sample that we've identified as M67 members, and I plot them together using the effective temperatures we've derived, this is the figure that we get. Already by eye, you can see that there is a sequence here for the M67 members. In an effort to describe that, we do iterative outlier rejection fitting to get a polynomial fit to that sequence of the stars in M67. This does raise the question, though, is it right to throw away all those other rotation periods? Thus far, they've passed all the other quality checks that we've had. The answer here it goes pretty deep. So I'll start with the injection recovery testing. So I have the results of our completeness. So this is the fraction of the time that we recover the right signal, given the injected rotation period on the x-axis and the injected signal amplitude on the y-axis. So each bin here is one region of parameter space, and the number or the color is the fraction of the time that we get the right answer, which we know is the right answer because it's what we injected. And then on the right, I can also do a similar analysis, but asking what's the false positive rate. So same axes as before, but now I ask the question, do we get a significant detection, and is it the right answer? And this case, we want this number to be as small as possible, because this is something that is the wrong rotation period, but by all other measures looks to be a true rotation signal. What this is telling us between these two figures is that when we plot all of our results together, we expect to see the true sequence of M67 behind a screen of these other false positive values. We can take this a step farther and say, why are we getting these false positives? And the answer lies in what we call the Lomskargel failure modes. So there's a single equation that captures them all pretty well. And it's basically just the result of the fact that we have an irregular sampling in time. So the parameters here are m and n, which are integers, any integer value. And delta p is a period of max power in the window functions periodogram. So basically, delta p describes the impact of how you've done your observations in time. So I'll go back to our original figure. We'll take our fit to the M67 sequence as the truth, and we'll plug that into our equation, and we'll choose one of the delta p values for our observations, which is 30 days in this case. And I'll plot what we expect the failure sequences to be. So essentially, where on this diagram would I expect the false positives to be if this is the true fit to the sequence? And this is what I get for a couple values of n. And you'll see that, especially for the shorter rotation periods, they're very consistent with these failure sequences. There are other ones that we can look at. So we'll do this again, but now for the delta p of 1 year, another impact on our observations. And just for completeness, I'm also going to include the classical case of a half period aliasing. If I add those onto this diagram, we'll see that the impact on our observations is a little bit different than the one associated with a month. It actually contributes to the scatter about the true sequence, and that's causing it to essentially puff up on this diagram. And then the half period alias helps us explain the rest of those short period ones that we reject. There are further steps to this analysis, but for the sake of time, I do have to move on. So we're going to take the 64 stars that it converges to, and I'm going to treat those stars as the only ones that we use as true. So I'll go back to our compendium figure that compiles all of our known calibrators for spin down. I'm going to add our M67 stars to it. Already we can see that across the board, the M dwarfs of M67 are spinning slower, or in some cases much slower than their younger counterparts. It's a good sign because that does mean that they will resume spinning down at some point, with our expectation, of course, but it's always nice to make sure that that's true. And yeah, but we could be more precise about this. So I'm going to take these data and I'm going to use them to compare against existing spin down models from the literature. The first set of models that I have here are a set of empirical relations that assume a solid body spin down. These are all calibrated to Praesepe and based off sun-like stars. And we can see that extrapolating those models' behaviors out to the M dwarfs is completely insufficient. This isn't too surprising because these are models that do not at all account for the fact that there's stalling in the spin down at some point. You do a little bit better if you do a physical model as opposed to an empirical relation. So now you're starting to incorporate some of the actual underlying physics of spin down. This is still a solid body spin down. It's still launched from the stars of Praesepe. It's a better match, but still not a particularly great match because this is a log scale for the periods to recall. If, however, we take our solid bodies models and we launch them from the stars of Ruprecht 147, we find that they provide an excellent match to the data. So what this is saying is that once a star resumes spinning down, it will spin down as a solid body. That idea might sound familiar because it's from the prediction of core envelope decoupling theory. So what we've done here is we've taken the stars of Ruprecht 147, which are the ones that we've seen have resumed their spin down. We've just evolved them forward in time. We find that they overlap extremely well with the stars of M67. So put that down as a point in favor of the core envelope decoupling theory. The final model we test is actually a core envelope decoupling model itself. By eye, it doesn't look like it's quite as good of a match, but there's a couple of things you want to keep in mind here. First of all, it gets the rough magnitude of the periods, right, which is the most important part. And the second thing you want to keep in mind is that this model was produced prior to the availability of other calibrators like Ruprecht 147. So when this model was produced, we didn't know when stars resumed spinning down. And yet they get it pretty close in terms of the rotation periods for M67. Another thing to keep in mind is that observations have shown that recoupling timescale between the core and the envelope, which would determine how that resumption of spin down occurs, is a very strong function of mass. And when they produced this model, they did not have the calibrators they needed to do that calibration for stars of this mass range. So again, in spite of that limitation, they've done a very good job for their prediction. And changing that would change the shape of this curve and could very easily produce much better match than they've already got. So all of this is to say that we've used this data to make a pretty compelling case for the core envelope decoupling theory in terms of describing M-dwarf spin down. So in conclusion, for the first part of this talk, we have generated a new catalog of over 1,800 members of the open cluster M67. We've identified the unresolved binaries, and we've derived effective temperatures for the late K and early M-dwarf members. We've measured the rotation periods of 294 of these members. We fit a polynomial to them to describe the sequence that they form in temperature period space. And we've used that data to show that the late K and early M-dwarfs rotate as solid bodies between the ages of 2.7 and 4 gig years, with rotation periods at 4 gig years that are consistent with core envelope decoupling models. And this is a last minute addition, but I got the email just this morning that you can now read all about all the details that I glossed over in the journal in AppJ. It was published this morning, not just accepted. Okay, so now we're going to move on to the second part. If we want to continue observations like this of other open clusters like M67, we're going to have to deal with the fact that these clusters are crowded fields. You can just see that by eye in some of the images I picked out here. I mean, it's basically by definition, right? The cluster is, well, the zoom is a little behind. There. The cluster is essentially by definition in excess of stars compared to the field. And on top of this, most clusters lie in the galactic plane, which is already the most crowded part of the sky. So if you want to do deep observations to get lower mass stars, you have to find a way to deal with the crowding. There's only two ways you can do it. You can do that. You can either put your telescope in space, which is very expensive, or you can use adaptive optics. So a traditional telescope system, you have the light passing through the atmosphere. It imparts a degradation in your image and causes the spot size that you get to essentially be larger. When you add the AO system, you have a wavefront sensor, which can measure that distortion. It hands it off to the real-time controller, which tells the deformable mirror to take a particular shape to counteract that distortion due to the atmosphere. And as a result, you get a sharper image than you had before. Unfortunately, a traditional system is sensitive to what we call anisoplanetism, which is to say this volume of the atmosphere is completely invisible to your AO system. So as the light passes through that portion of the atmosphere, it degrades the image of that star. And then because your AO system can't see it, it doesn't correct for it. And what that means is as you go farther off axis in a traditional AO system, your image gets worse and worse. A typical AO system will give you about 10 arc seconds before you start to see significant degradation because you're going off axis. That's a problem because open clusters on sky are going to be tens of arc minutes or even up to a degree in field of view. And so you need a field of view that's 1,000 times larger than what you're going to get from a traditional AO system. Fortunately, we have Tomographic AO. These are advanced AO systems that leverage the spatial distribution of turbulence to improve the performance, usually in terms of correcting that anisoplanetism issue. This is aided by the fact that the atmosphere is usually well described as a set of discrete thin optical layers. So instead of this whole volume of atmosphere, you have a couple layers where the light passes through that, gets some of its distortion, goes to the next one, picks up more of the distortion, and then reaches their telescope. The goal here is basically to just cross-match between what each of these wavefront sensors measure and use that to back out where the turbulence is vertically. So you use those commonalities and differences of what they see. An example of this would be that feature that I've circled here is only visible to wavefront sensor 3. So when you've done your analysis of the 3 wavefronts, you see that feature only in wavefront 3, tells you it must be somewhere in the free atmosphere. But there's another axis with information that's not being used here, and that's time. These layers typically have a coherent flow to them. Animation's not playing particularly well over Zoom, but if you take your telescope way out of focus, you can see this. In this case, there's supposed to be 3 layers visible, one moving up and to the right very fast, one moving down and to the right, and then one that sits in place and kind of evolves. So each of these are distinct layers in the atmosphere, and they are, yeah, I'll go to the next one. Hopefully that one plays better. Okay, so this is another case of that. There's just one layer in this case. So the atmosphere is moving up and to the left. That one's a little bit easier to see. And so this is information that we can use, right? We can leverage this to help us sort between which features in the layer belong to which, or which features in the wavefront belong to which layer. I'm going to take a second to note that we are doing this specifically for ground layer adaptive optics. So the goal here is to just sort the turbulence into 2 bins, the ground layer, which we view as the signal, and the free atmosphere, which we view as noise. The height of the free atmosphere itself does not matter. The ground layer is usually estimated as the mean of measurements from many widely separated guide stars. And so the goal is to reject the free atmosphere from our wavefront sensor measurements, which will then in turn give us a better estimate of the ground layer, improving the GLAO correction. And we've done this through what we've been calling temporal tomography. So there are a variety of ways that you can describe the shape of a wavefront. And for this portion of the talk, I'm going to choose what we call the Fourier basis. So we decompose the shape of our wavefront into its constituent sines and cosines. The reason we do this is because it turns out this basis is actually particularly amenable to describing motion across the aperture. Right, so I have the one-dimensional version of this. It's a sinusoid described by that equation. And you can see as you track a feature in that, this moves across your aperture. It's just a nice, clean, evolving sinusoid. describing that motion is actually identical to describing a fixed point oscillating up and down in time. Those two pictures are perfectly the same. And if you want to move faster, that just means you need to oscillate at a higher frequency. If I rewrite this equation in terms of physical parameters, then I can pick out what that temporal frequency is. And so for this one-dimensional case, the temporal frequency of that up and down oscillation is specified by just 3 parameters. K, which is the spatial mode of the sinusoid. That's a value that we choose because we're the ones constructing the Fourier modes. D, which is the telescope aperture size. That's fixed by whatever system you're using. And finally, V, which is the speed of that feature. So as long as you can measure the speed of the feature, then you have everything you need to calculate that temporal frequency. And the other thing to note is that as long as they have different speeds, they have different characteristic frequencies. I'm going to cheat and I'm just going to write the 2-dimensional version of this. We're just adding the y-axis, and we're now, instead of just the speed, we're now concerned about a wind vector. Okay, so we've taken our wavefronts and their slopes, we've turned them into these Fourier modes with our discrete Fourier transform, and we know that they're going to evolve with these characteristic frequencies. To see what those frequencies are, we go to the temporal power spectrum. So we've taken our history of data, we've applied another Fourier transform, this time in time, and we've now plotted that out to see what are the frequencies that this mode is oscillating at. And this is taken from one of our simulations, and I've identified one of the frequencies here. This is a layer in the atmosphere, and it's moving with a particular wind vector that gives it that characteristic frequency. So then the question is, can we identify these as layers that are free atmosphere or layers that are ground layer? To do that, luckily we have the CFHT weather tower. This is a small batch of instruments that are on the summit that provide more or less real-time measurements of the ground layer wind speed and direction. So once we do that, we can plug those into our equation for the temporal frequency. And then we know which are the peaks that'll be associated with the ground layer. These are the ones we want to keep. Once we've done that, the task is just to reject all the peaks associated with the free atmosphere. So basically everything else. We do this with what's called recursive filtering. So this is a pretty classical problem in signals processing of just taking real-time data, processing it some way to remove a component of it that you'd want to get rid of. And recursive filtering, you use your current measurement and the history of measurements that you have available. You can combine them in some way that removes that component of the data you're interested in removing. So we take our data, we choose our A and B coefficients here to make sure that it's removing temporal frequencies associated with the free atmosphere. When we do that, our temporal power spectrum goes from this to this. So we've taken the power associated with the free atmosphere in our wavefront sensor measurements, and we've removed it from our data. And so now, when I look at the wavefront sensor measurements, they look closer to what they would if there had just been a ground layer all along. There was never a free atmosphere. The question then is, how often are the wind layers on Mauna Kea different enough that they'll have separable frequencies? To answer this question, we look at archival data from the CFHT weather tower for the ground layer, and we look at archival data from the GFS forecasting model for the wind vectors of the free atmosphere layers. We calculate 2 values, each of which tell us how favorable the separation is in frequency space. To understand those values, I'll go back to our equation for the frequency. I'll point out that the numerator here is actually a dot product between 2 vectors. And so if we want to know how different the output of the dot product is, we want to look at 2 values, the difference in the direction and the difference in the magnitude. Magnitude in this case is being the wind speed. I'll start with the direction difference. So I plot all of the directional differences for the free atmosphere and ground layer over the past 5 years on Mauna Kea. So we have I'll split this diagram in two. On the left, we have the case where the separation between ground layer and free atmosphere is trivially easy because they have opposite signs. So they'll appear on opposite sides of the power spectrum. So you'll always be able to see, oh, this is definitely different from that one. The other case is when they have the same signs, they will appear on the same side of the power spectrum. Then what they have to have is different speeds for us to be able to separate them. So I take that half of the data set and I look at how different are their wind speeds. We find that usually they will have different wind speeds. At the very least, we can separate them in that case. Apologies. So in terms of direction of difference, difference in direction, I have 36% of all the nights make it trivially easy for us to separate between free atmosphere and ground layer. And then in terms of different speeds, I have another 31% of all the nights where the speed allows us to make the differentiate between the two. And so in total, 67% or 2/3 of all the nights on Mauna Kea over the past 5 years allow you to easily separate between the ground layer and the free atmosphere based solely off of the wind vectors of the layer. That gives us a lot of nights to work with. So the question then is, does temporal tomography actually net us any benefit? To understand that, I'm going to revisit our diagram of tomographic AO systems, and I'm going to talk about what we call the tomographic error. This is the measure of how wrong our estimate of the ground layer is, specifically because of the free atmosphere. To highlight how this works, I'm going to simplify our model of the atmosphere, and we're going to take 3 measurements of the wavefront. So it gives us 3 different realizations of the free atmosphere. So we have these 3 measurements, the shape of the wavefront, and in a standard GLAO system, you average them together, and this is what you would get, right? This feature is very strong, and so it kind of overrides the other 2 measurements. I'll bring back the truth for the ground layer from this example, and we'll say that is what we describe as tomographic error, right? We've made this error because we only have so many guide stars that we can average together. And that is the value that I'm going to be seeking to reduce with temporal tomography, and it will be the measure of how well we're doing. So if I go to our simulations now, I have on the y-axis that tomographic error. So again, smaller is better. The x-axis is the number of guide stars, the configuration of the AO system that we're using, essentially the number of measurements we're averaging together. And I simulate a variety of different atmospheric conditions. I have here the case where the free atmosphere is the dominant source of optical turbulence, and then a variety of different cases where the free atmosphere and the ground layer have different wind speeds to each other. This is for the standard GLAO approach. It's completely blind to the atmospheric conditions, and we can see that, right? It doesn't care how different the wind speeds are. This is still true even for the other cases where the optical turbulence shifts from the free atmosphere down to the ground layer. So all 3 of them look the same. This is expected for the unfiltered standard GLAO approach. I'm now going to add the results of using temporal tomography. There's a lot going on here, so I'm going to focus on just one piece at a time. This is the case where most of the turbulence is located in the free atmosphere. The circle points, the ones that are lower, those are the case where we're using temporal tomography to improve our GLAO correction. This is very exciting because this is telling us that temporal tomography, even a fairly basic approach that we've used in these simulations, can effectively double the number of guide stars that you're using. So like the 5 guide star system you might think of as standard GLAO system that you would use on Sky, it's performing at the level of a filtered 3 guide star system. And so if you had a 4 guide star, you only need 2 when you're using temporal tomography in this particular case. As you shift that optical turbulence down to the ground layer, though, we start to see the behavior change. So a couple of things I want to highlight here is that these circle points have now scattered out. So this means that we are way more sensitive to how different the free atmosphere and the ground layer are in terms of their wind speeds. And the other thing you'll notice is that this figure implies that you can actually make your estimate of the ground layer worse when you're using temporal tomography in this case. This is fixable. You can either just have this be a type of night where you would not use temporal tomography. So you have a GLAO system, you look at the distribution of turbulence for the night, there's a couple different ways you could do that. And if it's in the ground layer, you turn off your temporal tomography and use a standard GLEO system. The alternate approach is that you can actually develop more careful filter design. So a recursive filter is nice because you can actually design it to have essentially an arbitrary response. And so we can actually tune that filter to reduce the amount of power that we're rejecting at a given frequency. This is important because it turns out that the free atmosphere and the ground layer, while they're concentrated at different f sub t values, they do have power at all frequencies. And so what's going on here is that this filter is too aggressive. It's actually rejecting some of that ground layer power. So you can just bring that scale that filter back, and you'll address that issue. It'll bring all these curves down to at least match the non-filtered case. Right, so this is a problem that we're not really worried about. The question then is, how often are these distributions of turbulence occurring on Mauna Kea? And if we look at the seeing monitor data for the past 5 years, we can look at how that turbulence is distributed. We find that half the time on Mauna Kea, the ground layer is the dominant source of turbulence. That's a great case for GLEO in general, not so great for temporal tomography, but that's okay, because the other half of the time are the cases where we can actually net some benefit from using temporal tomography with our GLEO systems. Okay, so in conclusion, for the second part, we've demonstrated that the winds are favorable on Mauna Kea for temporal tomography 2/3 of the time, and the turbulence is distributed favorably about half the time, which gives us a lot of nights to work with. We've demonstrated that a quarter of the time, even our naive approach that we're using at the moment lets us effectively double the number of guide stars that you're using, which is a huge impact, particularly for smaller telescopes, where you want to reduce the number of wavefront sensors you're using because that makes the system cheaper to build. And there's a lot of future work that we're interested in doing. So as I mentioned, it's a couple points to more careful filter design is definitely something we would like to push further on. More detailed simulations to improve those as well will help us better understand the limitations and gains that we get from temporal tomography. And then there's some on-sky testing that we have been doing. We're getting some pretty confusing results at the moment, but we'd like to push those further. There's a lot of stuff going on there we'd like to see test out. And then finally, I've been looking at ground layer AO specifically, but the wind's vectors change as a function of altitude. So it's possible we can get higher vertical resolution here. We can use temporal tomography to aid other AO systems like multi-conjugate AO or laser tomography systems. Okay, there are many people I would like to thank for getting me to this point today. Too many to list all of them, so I will choose just a few. My advisors, Mark, Jen, and Eric, you guys have been incredible, and I would not have made it this far without you guys. The Hilo grads, both new and old, in particular Jess and Max, you guys played a huge role in making Hilo feel like a home. And then I will also say thank you to my cohort, Zach, Deep, and Ashley. Can't wait to see where we all go from here. Okay, with that said, I will leave you with conclusions from both parts of this talk, and I will open the floor for questions.
So I guess the way this will work is that we'll take questions from the grad students and all the audience, and then open the floor for other questions from people who are not on the committee. And then after that, we'll go into a closed session and the committee will ask more questions. So Miles, go ahead. We'll start in Hilo.
When looking at the tomography for the wind layers, when you're looking at the whole picture, did you find any correlation between certain wind speed frequencies and the Fourier modes? Did you find that, at high wind speeds, you had higher frequency modes or any correlation like that?
That's a good question. So we did find that the speed at which your AO system is running has an impact on this. And as the layer gets faster and faster, you'll start to see that the power actually spread in frequency space, which makes that problem challenging. And so there's a relation there in terms of how fast the system is running versus how fast the layer is moving. But as you increase the speed at which your AO system operates, you can address that issue. Other than that, they just kind of have their own sets of Fourier modes, and they operate independently of each other.
Thank you.
So way back with the M dwarf spin down stuff, when you showed that great plot of rotation periods, it was pretty easy to explain the like half period aliasing and the spread, but there was a lot of points with longer rotation periods. And I was just wondering if you had either an intuitive sense or if you've had time to look at what those might be due to.
Yeah, so you're talking about these points up in the upper
Yeah.
left. This is one of the things that I kind of glossed over.
Yeah.
We do take a look at those, and they are also Lomskargel failure modes. You
Okay.
can do like an inverse analysis to what we were doing, where you say this is the observed period and assume its true period is here. And you'll find that if you assume it is if you treat it as a Lomskargel failure mode, its true period actually lies along that sequence. But we don't do that. We don't take that extra step because you can't for sure say that's the case. You never truthfully like really know that's the case. But the fact that they all kind of are still consistent with that sequence is why we're able to say we think those are incorrectly measured rotation periods.
Okay.
Any other graduate students in Hilo or on Zoom or in Manoa? We can't see the people on Zoom who might have their questions or in Manoa. So if somebody on Zoom or somewhere in Manoa can, have you seen anybody with questions? Just shout them out. Right.
So I think if Manoa can unmute and if Zoom people can raise their hands if they have a question, then I can unmute them.
Great, thanks. Great.
I think Kenji has a question.
Oh, Kenji, sorry.
I guess my question was on your HR diagram.
Mhm.
You kind of fit the different stars, but at least up by eye, it seems like there's a split between between like on the left plot. There seems to be your color distribution and what looks like an extra one on top of it. Is that real or is that improper filtering of the background stars?
Which
Like the gray points seem to be above, like have its own distribution above of the colored.
so these are the if you're referring to this kind of second sequence above, those are the unresolved binaries. So they're uncharacteristically bright because there's actually two stars there that are giving you both flux from both of those. And so that's what shifts them up or brighter on that color magnitude diagram. For these, they are also binaries, but they're probably white dwarf binaries. So the white dwarf is making them very blue and not so much a lot brighter. And that's why they appear to the left, not so much below as they are to the left of the sequence.
And they were just rejected in the.
Yeah, and we exclude those from our analysis because binaries that are close into each other will have tidal forces that impact their rotation history, and we save that for future work. So
do you exclude them just in color here, or do you exclude them using like Gaia matrices and things?
we did take a look at the Gaia metrics for that. So the Rui values for all these stars, they're all pretty consistent with being single stars in that space. We only use the photometry. We did check all the ones that are binaries by that Gaia measure are also tagged as binaries by this approach.
Hey, Ryan. Great talk, first of all. Looking at this plot, it looks like there are some pan-stars, single stars that appear to be binaries in the Gaia color magnitude diagram. Have you looked at those? It's just a few.
I have not looked at those in detail, but yeah, I've noticed that there's like probably 3 that in Gaia seem to be binaries, but are tagged as. And so it's possible there's a difference in the spatial resolution that gives you some issues there, but it's not something I've looked at.
Fair enough. Congrats.
Any other grad student questions on Zoom? We'll open it up for anybody else.
Mike Liu, John, I think I see a couple hands up.
Okay. Luke has a question here in Hilo, and then we'll go to this one.
I'm curious about the scale of turbulence and how the tomography results will change with much larger aperture telescopes. Do you have a sense for that?
Yes. Let's see. You mean in terms of like the tomographic reconstruction itself here? So like as this telescope aperture increases, yeah. So the I guess the term that we use to describe that is the metapupil, is the width of the telescope, but applied to the free atmosphere itself. If you increase that, you change the way in which this overlap occurs, and so you have to be a little bit more careful about how you're doing that kind of triangulation between the different things. But the geometry, the basic principle behind the geometry of just these angles will give you this separation at this height. That all basically stays the same.
On Zoom.
Hey Ryan, this is John. It's a great talk, and I have one question about your rotation period versus color fits. It seems like a lot of power was given to the coolest M dwarf that had a longer rotation period. Did you do any tests removing that point that's all the way on the right-hand side of the diagram to see how it may affect some of the conclusions?
Yes, so that's where this confidence interval comes in here. So we did a bootstrapping approach where we took our full sample of all those, almost 300 rotation periods, and we sampled randomly from that with replacement to generate, and then applied a fit, and that's how we get these confidence intervals. And so you can see, at that very faint end there, the confidence interval kind of really blows up on you. I think it's because it's one of the only stars at that end. And so that's how we kind of account for that without trying not to give it too much weight in that case.
Thanks.
Hey Ryan, I had
Anyone
a question about your very last slide. The last plot, I should say, which you showed the distribution of the turbulence versus the free atmosphere. Yeah, this. I was wondering about as you know, there's a big push to put GLAO on telescopes, multiple telescopes on Mauna Kea. And I was wondering about the implications of this in terms of actual operation of those systems. If it's only 50% of the time that they're making much difference, that seems like an extra complication.
So it makes a difference in kind of all of these cases. I'd say it makes the largest impact when the ground layer is dominant. Because if you correct just the ground layer and the ground layer is the only thing that's giving you any turbulence, you're going to get a very good image out. What this figure doesn't capture is that the ground layer still contributes or can contribute a significant amount to the seeing, even when the free atmosphere is the dominant layer. And so there's still a case for using GLAO in that case. So I should have prepared an extra slide for this, but GLAO will essentially shift your median seeing value by down by 0.3 arc seconds. You go from 0.7 median seeing down to like 0.4. And so it, impacts kind of all your observing cases that you might be interested in for that.
Any other questions from non-community? Mike?
So for the younger clusters, for the M stars, looks like some of them had some of the stars that spun down, others were still spinning really fast. And they look like there's a lot in between.
Yes.
Some stars got the memo to spin down and others didn't.
Yeah. So to repeat, the question is essentially why are some of these M dwarfs here spinning really, really fast while others are spinning kind of on that slow rotator sequence? And the answer there is that these clusters are young enough that we're still seeing the impact of the initial conditions. And so these are the stars that were born spinning very fast and have not had long enough to converge onto the slow rotator sequence. The higher mass stars will usually converge onto that sequence faster than the lower mass stars. And so that's why you're seeing more, the problem get worse as you go to the lower mass stars in this case. And so if we observe a cluster like M67, we see that those slow rotators or the fast rotators are now all spun down by that point, and they've all forgotten their initial conditions and converged.
Okay. Any other questions? Okay, let's thank Ryan again, and then we'll. So we'll ask people to leave the room and my acceptance.